All right, welcome back, everybody. So this is part two of the Computations with Discrete Fourier Transforms videos. So last time I showed you how we could compute the coefficients for a discrete Fourier transform by hand. And you can imagine how terrible that will become if we have to do this for more than, say, half a dozen points. This is going to be a very lengthy computation if we have to do it by hand, so we need to be able to turn this over to the computer. So here's where we're going to start. We're going to do the same computation we did in the previous video, but we're going to do it in MATLAB now. So let's go ahead and set it up. So once again, I'm using MATLAB Mobile here. And what we're going to do is we're going to start by collecting some sample points. Oh, come on. Silly thing. Disconnect and then reconnect. So, as we wait for this guy to come back up, what we're going to do, we're going to take the interval from 0 to 2 pi and space it out into a certain number of points. And n here, I'm going to go ahead and say that's 4. So what we're saying is we want 4 sample points. And I'm going to create this vector points as a linspace, so 0 to 2 pi, and we're going to do this for one more than the number of sample points, because remember, we are going to start repeating ourselves once we hit the end of that interval at 2 pi. So I really only want the 4 points that came before the last one. So little x, I'm going to go ahead and say, is points of 1 to 4. And that's going to create this smaller vector just by 1, but it is going to have 4 points to it. And what I'm going to do is I'm going to make my sample vector f like I would in the example that we did by hand. And this will be computed thusly. So I'm still using the same function x cubed times 2 pi minus x, but I'm doing this in vector form. So this is my sample vector that I'm going to create. Right. So if I were to plot this, I'll do this x by f, and I'll do this in little red circles. So R0 or RO is red circles. And voila, I have my sample points. They're a little bit tricky to see, but I can go ahead and, well, I'll put it back up there. I'll show you that this is going to be stringing together the points that I need for reconstructing the following function. And this time I'm going to do it with a true linspace 0 to 2 star pi, and I'll do this for 500 points. And what I'm going to do is create a big vector y, which will be exactly the same function now, but it's going to kind of show you how to interpolate those points so you can see that this is actually creating the function that we want. So yay, lots and lots of points here now. So plot little x, little f, R0 or RO, and then big X, big Y, and I'll plot this guy in, I don't know, maybe green? No, I'll do the sample points in green, and we'll do this guy in red. So that will be just R. And indeed, you can check out your sample points here. The sample points do lie on this cubic curve now. So there should be 4 of them. There's one at 0, one at pi over 2, which is about 1.6-ish, one a little after 3 at pi, and then one more at the crest of this curve, which is it's close to about 5. It's 3 pi over 2. And then you'll notice that it does come back down and hit 0 at 2 pi as per the root of the function. Great. So what now? We're going to try to do a Fourier transform of this function. We're create a discrete Fourier transform. And this is actually done very, very slick, very, very easily in the computer. I'm going to name this guy capital F. Usually the convention is to use capital letters for your Fourier transform variables and lowercase variables for your original signals. And what we're going to do here is use the function FFT of the sample vector. Okay, so FFT stands for fast Fourier transform, and this is the algorithm upon which modern technology is built. Right, this is a very, very efficient way of computing the discrete Fourier transform coefficients. It's much faster than doing it the way that we did in the previous video. So when we do that, it should spit out the 4 coefficients that we need. right? And in this case, sure, we're going to see exactly the same figures as before, and these are complex numbers as we know or we're supposed to get. And notice f of 2 and f of 4 are the two complex conjugate coefficients from last time. Those were C1 and C3 in the previous computation. But I do now have my Fourier coefficients, and what I would like to do is show you how to reconstruct the functions using the complex exponentials instead of the original signal, which we will not have access to in general. So what I'm going to do is I'm going to create the matrix of primitive vectors. So I'm going to create my basis matrix. Primitives, I'm going to set to be zeros, n by n. Or I could just say n and it'll create a square matrix of that size. But what we're going to do, I'm going to run a double for loop here, a nested for loop for double I, double j, and you're going to see particularly now why we need to use these double i's and double j's for our indexing variables to distinguish them from the complex number I or j. So we're going to fill in this matrix. So not primitives, but the ijth entry here, this is going to be the, it'll be the the nth power, or the jth power of the ith primitive root of, or the ith root of unity. So this will be exponential, and this one needs, I believe this will have the negative in front of it, so the negative I. I'll do I minus 1 times jj minus 1 times 2 times pi over however many points I have. I need to equally space these guys. Right, so this will be primitive there, end both of the loops, and check it out, the primitive, this will produce exactly what I wanted. So in that first column, so primitive 0 by 1, the first column is all ones. Primitive colon by 2, the second column is alternating 1i minus 1 minus I. And notice that it's a negative, it went the other way, sorry. So I suppose I need to go the opposite way. But if I check out the help page on FFT, notice that the way they define their primitive vectors, they actually go clockwise around the circle rather than counterclockwise like we did in our previous example. So this one, we need to use the minus sign in front of the frequencies on this direction, just by virtue of how MATLAB computes the discrete Fourier coefficients. So this is correct, right? It's going to be backwards from what we did in the previous example, but it's still going to give us the same results. So let me show you. We have the primitive vectors now, and I'd like to create my approximation, or I'd like to recreate the sample vector. Sample is a 0 vector of size f. Okay, so this is just, size of f? Oh, zeros. 0 vector of size f. So zeros of that. And what we're going to do is just say that the sample vector is going to be whatever weights I need to throw in front of each of the primitive vectors. And the way that this works, if you think about how matrices multiply into vectors, this is going to be the primitive matrix times, and if I remind you that the the discrete Fourier coefficients are given as a row vector. So in order to make sure that these guys are going into the correct columns, I'm going to multiply primitive times f prime, and then I'm going to have to divide this by the number of vectors I have. Remember, this is by virtue of the inner product that I had to use on my sample vector space. So the sample vector gives me these 4 points, and I can plot them. Plot x by f and do that in red with circles. And then I'll do the next one, little x with sample, and I'll do these in green pluses so you can see them together. And we will see that these give me exactly, I'll blow this up, they give me exactly the same locations. So I'll try to shrink it again and then try to blow it up so you can see what's going on there. See I have a little red circle containing a little green cross. Right, and that's exactly what we were hoping for. Okay, so this is how you reconstruct this guy, but it's not producing something that's terribly, interesting for us. I mean, it's not showing us what the difference is between what we just made and what the original signal was, until we can see what's happening in between these two functions. So remember that we have this x vector, size of x. This is the 500 points between 0 and 2 pi. What I'm going to do now is recreate, kind of like in the previous video where I had this, this picture of what's happening in between the sample points. We're going to create the same thing. We're going to do that in MATLAB here. So remember that x and y were the original function, like the pure, like, continuous signal. I'm going to do the same thing now, but we're going to use this for what we're going to call an approximation. All right, so approx is zeros, not zerps, of size x. Oh, zeros of size x. What do you mean it must be integers? Equals zeros. Oh, of size of x. That's what it is. Size of x. Okay. Now, here's the trick. We need to remember that we are using a full complex function in here, not just a discretization of one. So what I'm going to do, I'm going to run a for loop for approximation, and we're going to fill in the approximation vector, which is going to be a nice 500 point long vector, or 500 column long row vector. And we are going to just keep appending to it f of ii, the Fourier coefficient. We're going to divide by the number of points we have. Remember our inner product, right? The inner product we're using needs to use that divide by n. And we're going to multiply this onto the function I times ii minus 1 times big X. And remember, x is big X is taking care of all the points between 0 and 2 pi, so there's no other weird scaling that I have to do on this guy. And I can try to plot this now. Plot big X with, or let's do this with our points. So little x with f, and do this with red circles. And then we'll use big X with big Y to show you what the original signal looked like. And then we're going to use big X with approximation, or with approx. We're going to do that in, what color do we have left? We're going to do that in green. So so sample points we'll do in red. No, we'll do in green. Sample points we'll do in green. So go! Then blue for the original function, and then, no, we'll do blue for the approximation, and then red for the original signal. And we plot these guys together, and notice what happens. The blue, so the red curve with the green green samples on it, that's the original thing that we had, right? We are trying to figure out how to create the same sample vector using different functions. So instead of using a polynomial to approximate this guy in the red curve, we're actually using the complex exponential functions. And this creates a whole bunch of sines and cosines, or combinations thereof. And you'll see that MATLAB actually suppressed the complex, or the imaginary parts of this approximation. But I want to point out the imaginary parts of the approximation sample vector should be quite small. So if I go through, let's see, the imaginary parts, they're going to be quite small near the quarters. So at 125, entry 125-ish, these guys should be getting pretty small. There we go. Yep, right here in this line, it goes from 0.9686 to minus 0.3268. But the point is that we've suppressed that output. And I believe, since that didn't happen on a sample point in particular, that this is okay. So we can actually plot that. Let's do x with big Y, and we'll do that in red. Then we'll do x with the imaginary part of approx, and we'll do that in blue. And we'll show you that the imaginary part should be hitting 0 at all the right locations. So if I go back and include the sample points as well, we will also hit zeros for the imaginary part. So there shouldn't be any complex numbers as part of as part of our approximation approximate reconstruction. And sure, you can see wherever there is a red point, there is wherever there's a circle for a sample vector, you trace that down to the x-axis, and I think you can convince yourself that those occur on the x-axis. They do produce 0 imaginary part. Now, that's all well and good, but what if we needed more points? So let's do the same thing, but let's do this for, I don't know, maybe 32 different points now. So we're going to create points again. This is lens space from 0 to 2 pi, n plus 1. Great. And we're going to go ahead and throw away the last one. So x is points 1 to n. I'll suppress that. And we're going to go ahead and create the sample vector little f once more. And this is, again, x dot caret 3 dot star 2 times pi minus x. That will create my sample vector, and I can show you, yeah, there's the sample vector, it exists. And if I plot x by f, you can see more clearly this time that we are indeed creating an approximation of the original signal. It's almost impossible to see that this guy is kind of strung together. We'll do that in red circles again. Oh, shoot. Do that in red circles again. It's easy to see now, or easier to see, that this guy is a better approximation of the original function to begin with. So let's have a look now. We would like to create the Fourier transform coefficients, the DFT coefficients. So we're going to use FFT of little f to create that vector. And we are going to now reconstruct the function with approx. So remember, approx, we're going to start with zeros. And this will be the size of the big X vector, because we're trying to recreate a nice continuous function. But we're going to do for I, we have to recreate our primitive matrix as well. Primitive, we're going to go ahead and say that this is zeros of size n. And we're going to do that that nested for loop again. So I goes from 1 to n, j goes from 1 to n. Primitive iijj is going to be exponential minus I star ii minus 1 star jj minus 1 times 2 times pi divided by n, right, to get the appropriate scalings. And we'll kill that off. So primitive, I'll just show you what it looks like. It's gigantic. It is a 32 by 32 though, so size of primitive is a 32 by 32 matrix. And we're going to recreate, if we wanted to recreate the sample signal is going to be primitive times, what would it be? It'd be f prime divided by n here. And I can show you, oh, primitive? Yeah, primitive. And we can actually plot this against xf with red circles, and then x sample with maybe green crosses again. Green pluses. Oh, sample. Okay, so I can't type. We've established that. There we go. And this will create exactly what you expect. It's a whole bunch of red circles with green crosses in them. We have reconstructed the original signal with a complex set of complex basis vectors. That was the whole point. Okay, so let's continue then. Let's see what approx looks like. So we've already set approx, right, so approx is this 500 by, or 1 by 500 vector, so a row vector. And we've already set it to 0, so just show you, approx is a whole bunch of zeros. But this time, we're going to go ahead and run the same thing. Approx equals approx plus whatever f of ii is divided by n times exp, or the exponential function, I times ii minus 1 times big X, right? Remember, we're not using sample vectors anymore, so we don't need any weird scalings. And that creates the approximation function, and we'll play the same game, x by f with r0. Then we'll do x by big Y to show you what the original function looked like. So sorry, these guys should be green sample points. And then red for the original curve. And then we're going to see what happens if I plot x with approx. And this will give me the following figure. Oh boy. So notice there are quite a few more intersections this time around. But the point to really take home is that these green sample points that where we sampled the original red curve intersect the blue curve at exactly the same locations. Yes, there are many more intersections than what we've already what we put in here with green, but the point is that we do see exactly the same outputs on the blue curves when we look at the sample points as we do on the red curve at the sample points. And that is what this discrete Fourier transform is doing. It is trying to recreate a sample or a sample vector from an orthonormal basis. All right, and you're going to be using this in your project to figure out how to kind of take these Fourier coefficients, these guys in F, and say, okay, I want the original signal, but I want low frequencies to show up. So you can actually filter this guy by saying, okay, I want to make sure that all of my frequencies above a certain level are gone. So you'll actually notice this. Look how much smaller the size of the coefficients is for vectors for the frequencies that come later in the vector. So compare let's say F3, which is on the order of 272-ish, or I can say the norm of this guy, the length of this guy, so absolute value of the answer, is roughly 311 units away from the origin in the complex plane, as opposed to f of, say, 30. Right, this is much further down the road here. F of 30, absolute value of f of 30. Sorry, do I want that one? I want f of like 15 or so. Do f of 15 or 16. Yeah, look how much smaller this guy is. Right, remember, this is a consequence of aliasing, right? So f of 15 and f of 2 actually, f of 3 and f of 14 will actually have the same size due to aliasing. But if I look toward the center of this this vector, and technically I suppose I could plot it. Plot f, and it'll show me what this vector looks like in the complex plane. So it's not very informative, is it? So unless I kind of turn it into a scatter plot. Plot f with, let's say, red circles. Then this will just go ahead and show me, look at where this guy clusters. Like there's a big spike off to the right, which corresponds to the 0 frequency. But then everything seems to cluster around maybe 12 or so in the complex plane. And that's in the middle of my frequency, the middle of my frequency terms. So that's around 15 or 16 where that happens, or f of 15 or 16. Actually, f of 16, if I check that, yeah, f of 15 and f of 16 have the same size. This is what it looks like to me. They look very, very similar. But the point is that these strengths get much lower the higher you go in your frequency. So actually, yeah, I could actually plot absolute value of f. And notice exactly how that happens. Have a look at the frequencies in the middle there. Those guys get much smaller, right? They contribute much less to the signal. So you can filter out your signal by getting rid of those higher frequencies, so getting rid of those higher frequencies and leaving a whole bunch of other frequencies when you reconstruct the signal. So you won't get a faithful representation necessarily, but it is going to get you most of the original signal. And this is how we do a lot of compression, or how a lot of compression algorithms work these days. Right, you use a low pass filter to get all the low frequency signal information, and then you just kill off all the high frequency information, and this retrieves most of the original signal. right? And because this is your project, I'm not going to show you how to do that. I want you to start thinking about how you would do it on your own. So at this point, let's go ahead and end the video. And we have officially finished chapter 5. So yeah, I think, yeah, we're going to chapter 6 now. No, we're skipping chapter 6. It's more of an application section for engineering, and it's actually, it's interesting, but at the same time, we need to be able to look at different applications more toward the singular value decomposition. And that has to do with eigenvalues and eigenvectors of non-square matrices. And again, we're going to look toward a matrix factorization to motivate how we think about algorithms from that standpoint.